So, welcome. So, let's get on with this next bit. This next bit's like, it's all potentially test questions, but this next bit's important. So, we're going to be using Gauss's law to determine the electric field caused by some specific charge distributions, and we're going to show the charge distribution. I'm going to step through them for a minute. We're going to have the point source of charge. We're going to have a ball of charge. That means a ball of charge means it's filled in the inside as well. We're going to have a shell of charge, and then we're going to have a rod of charge, and we might even get to a wall of charge. And in each case, we're going to use Gauss's law to figure out how we work out the electric field at an arbitrary point. And it's through the clever use, the mindful use of a Gaussian surface that's appropriate for that physical situation. So what we're going to do, we're going to look for Gaussian surfaces that have the following properties. And the first property we want is we want a pen first of all. First property we want it to be electric field to be constant over the surface entirely, or at least some well-defined part of the surface. If it's a cylinder, we want it to be constant over either the sleeve of the cylinder or the ends of the cylinder, or something like that. And then we're going to find that we're going to say we want a Gaussian surface that gives us a dot product, which can be expressed as a simple algebraic product of E and dA. So we want the electric field E and our little area vectors to be parallel wherever possible, or we want them to be at 90 degrees wherever possible. So if they're at 90, then what that means is that there's no flux through that surface. If your area vector's in that direction, and your electric field's in that direction, it's like looking on the end of the card. Area vector, electric field, no flux, or 90 degrees. But we don't want 45 or 33 1/3 or something. We want them to be either parallel or perpendicular. And we want the electric field to be, can be argued to be zeroed over a surface. If we can argue that, that's great. And we'll solve. So, as it say, you know, if you had never seen these things before and we showed you Gauss's law, then you could maybe intuit what to do, and it would be a real act of insight. But, you know, this is a course that's designed to train you in things. So rather than trying to invent things from first principle, we'll show you the majority of the common situations. So to some extent, we're showing you, we're developing the answer to things that people know, but that's the way life is. So what we're going to say is, the question would say something like, all right, imagine a charge here, Q, and a point here, P, and I want you to figure out the electric field at that point. And that's all it would say. The point P is so many meters away from Q. Q has so many coulombs, positive or negative, get on with that. So then you got to pick the Gaussian surface. And what you're looking for is a Gaussian surface with those things. The two big things tend to be, can I get my area vector and my electric field vector to be parallel? And can I get my electric field vector to be constant? And if I look at this, because I'm picking a spherically symmetrical Gaussian surface, like a bubble, that's symmetrical about the point source in charge, then that means that the radius to the Gaussian surface is always the same value. So my E on that surface is constant. Everybody okay with that? Same distance, constant E. And then the next thing is, because the area vector is perpendicular to the surface, it must be radial from the point charge. And my electric field, of course, is radial from the point charge. So these two guys are parallel. So by picking this spherically symmetrical, cylindrical, spherical shell, I've satisfied those two Gaussian surface wishes. So it makes my life much easier. I'm just going to use Gauss's law no matter what. Just by using a good Gaussian surface, life becomes much easier. So we pick a spherical Gaussian surface centered on the point of charge because E is parallel to dA on that Gaussian surface, and I've shown you an example here. And E is constant on the surface. So I state Gauss's law. E is equal to the flux is equal to surface integral of E dot dA, which equals Q in over epsilon naught. And now I am going to use the middle bit. Before we were not using the middle bit, now we are going to use the middle bit. We're not interested in flux anymore. I mean, we're interested in it, but we're not going to specify it. We say, well, okay, we just know that E is constant. So E can come out, so it's E integral dA. Oh, well, okay. I know that the surface integral of a sphere is 4 pi r squared. That's very nice. I've gone from two vectors to basically two things that I know multiplying each other. And these guys together equal Q in over epsilon naught. So then let's rearrange solving for E. I don't care about flux anymore. E is equal to Q in over 4 pi r squared epsilon naught. Then my next thing is I turn around and say, you know, in physics the tradition is to talk in terms of Ke. So I know that Ke is equal to 4 pi over epsilon naught. And look, there's a 4 pi, and there's an epsilon naught. So E is equal to Ke Qn over r squared. And isn't that the identical equation to what we learned last chapter? So we've just used Gauss's law to justify that equation. Okay. So a typical test question would have numbers in. In a typical test question, I would say, using the method of Gauss's law as shown in class. And what that means is, I want to see this. If I ask you, what's the electric field this far away from a point source of charge, you can just use the equation. But if I say, using the method of Gauss's law as shown in class, I want this methodology with, then you put numbers in, or however you want to do it. But you've got to show me the integral and the steps, and you know. So this is going to come up. One of these is going to come up. So I want you to know it's coming and get ready for it. My idea is, as we did a little bit in Physics 1, my idea is if I tell you something's coming that's a bit of a challenge, you've got a choice to make. You either turn around and say, I'll ignore those points, or I'm going to go for those points. And if you go for those points, you'll learn this bit. And my theory is that the next time I give you something that's a little bit challenging, you've learned this so you can build on that foundation. So rather than maybe it'll come up, maybe it won't, and you're not, you might be putting this to one side. I'm trying to encourage you to make this step. And you'll get stronger and stronger if you keep making these steps. So a 10 coulomb positive charge is located at the origin using the method of Gauss's law as shown in class. Determine the electric field at a point 3 meters from the point source of charge. There's a typical question. Can you do that for me, please? You can look back at this methodology and just mirror it and just write it out for me. We're back, and let's see how this goes. Give you just until the 4 minutes is up, and then we'll get started. So let's stop this. Let's see what people are saying. A, okay, pretty well. Everybody's saying A. So let's see how we do this. So what you do is you say, there's my point source of charge, and I'm going to do a spherical Gaussian surface around it. How do I know to do that? Because I've practiced. And I know on spherically symmetrical things, it's a good way to go. I have my radius r, my point of interest. That would mean my electric field here is parallel to my little bit of area dA. Electric field. And I say, oh, well, flux is Gauss's law. The flux is equal to the surface integral of E dotted with dA, which equals Q inside the Gaussian surface over epsilon naught. And I can say, well, actually, you know, E is constant on this Gaussian surface. Not all Gaussian surfaces, but on this spherical Gaussian surface. It's constant, so flux is equal to E, the integral of dA times, which equals Qn over epsilon naught. And I know that E is parallel to dA. So I can say that my flux is equal to E. I'm sorry, that should be like that. So I can say that is equal to that times that, and these, which equals Qn over epsilon naught. And then I say, well, you know, I can say that dA sorry, the integral dA is equal to 4 pi r squared. So I can say, well, my flux is equal to E times 4 pi r squared, which equals Q in over epsilon naught. Don't care about my flux anymore. So I can say my E is equal to Q in over 4 pi r squared times epsilon naught. And I can say, oh, remember that epsilon naught, sorry, KE is equal to 1 over 4 pi epsilon naught. So that means that E is equal to, well, 1, there's 4 pi and there's epsilon naught. So that's KE Q in over r squared. So then I've got to put some numbers in. So let's go over here. So E is equal to 9 times 10 to the 9 times Q in, which was plus 10 over r squared, and r is 3, so that's going to be 3 squared. That works out nicely, those cancel. So that would be 1 times 10 to the 10, and it's an electric field, which is Newton per Coulomb. So am I right? 1 times 10 to the 10. That would get you the points. I know sometimes people, they try and work backwards, and it doesn't match up in the middle, and I'm kind of ruthless about that. It's kind of like, unless the steps are there, you know, I'm sorry, I can't follow it, boom. So, and I actually, if I could take points away when people work backwards, I would. I feel bad doing it, but I'm going to spend 10 minutes trying to figure out what you did to try and give you credit for it, and then realize, oh no, they just work backwards. So you know, make sure it's a logical steps. You find stuff just appears out of nowhere, and you know, stuff disappears, and it's a bit frustrating. So if you don't know it, you know, just, you know, hey, next time, you know. So is the next example? Yes.
I'm slightly confused as to how you can just assume the shape of the surface.
I'm a free person, so it's as simple as that. I can do any Gaussian surface I like. Now, why do I pick that surface? Is that the intent?
No, like I don't understand why you can just choose any of them.
Because, are you saying why is there a thing called a Gaussian surface?
No, I understand that, like, I understand them and I understand that there's different kinds. I just don't understand why you can apply any of them to any situation.
Oh no, I can only apply one of. Oh, that's all. It's because the basic law, because that's a law.
Yeah.
So if you have a charge and you have a Gaussian surface, that law applies.
Yeah.
Now, if I pick a good Gaussian surface, that law becomes relatively simple to apply.
But why are you allowed to pick? Like,
So an equation will work no matter what numbers I put in.
yeah.
Why am I allowed to pick which numbers I like? It's just a different example. So a Gaussian surface is an abstraction, and I can imagine, it's a visualization. I can visualize any one I want. Okay? If I visualize good, it works easily. If I visualize bad, it works hard. But it is an abstraction. It's not a thing, and I mean, I'm not, I remember being introduced to this thing called a Boolean surface, and it was like, it was so abstract that one of my classmates said, why doesn't the Boolean surface fall out of the end of the rod? And the professor was like, you know, it was kind of comical in a way. But the realization was that it was like, you know, we're so used to dealing with concrete things that abstract things and the freedom with abstract things comes as it's not easy for us. So I mean, so all I'd say to you is, you are free to pick a Gaussian surface. And if you pick a good Gaussian surface, this law becomes easy to apply. And if you pick a poor choice of a Gaussian surface, this law still applies. And if your math skills are good enough, you will get the right answer, but you'll have to work really hard for it. Okay? But the law applies, so any Gaussian surface will obey the law, will be part of this thing. Yeah? Okay, cool. And the Gaussian surface is like it's a methodology. I don't know if I've missed your point, but that's kind of like, you know. Cool. So on this, can you see how this question here on the left is the same question? It's like, again, we've basically got a ball of charge, but again, we're going to put a Gaussian surface symmetrically around it. So it's going to give us the same answer. Okay, is this the one where I have a page? Let's just step into it. Did you? Yes. Okay, let's just step into it. So auto save and load now, cancel. Wait a minute. Come on, I don't want to. Okay. So then let's say we have a ball of charge. And let's say that this ball of charge is 2 meter radius ball of charge. And I'm going to call, in my like derivation thing, I'm going to call that A, just in my math. And I have a point of interest. The point of interest is here. I'm going to call that a distance r. Now, can you see from a symmetry point of view, I want a spherically symmetrical Gaussian surface again? Yeah? From that point of view. And can you see how I would say, well, okay, well, flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. And so, you know, yeah, E is constant on GS, and E is parallel to dA. There's my E, and here's my dA on Gaussian surface. So this simplifies to the flux is equal to E, the integral dA, which equals Qn over epsilon naught, and this is equal to E times 4 pi r squared, which equals Qn over epsilon naught. And then I say, okay, so E is equal to Qn over epsilon naught times 4 pi r squared. And I realize that Ke is equal to 1 over 4 pi epsilon naught. So E is equal to Ke Qn over r squared. And you go, whoa, what happened to A? I never used it, okay? Because Qn contains everything, okay? Now, that's the same derivation. Those two problems that we just did, exactly the same. But just by deciding that my point of interest is not outside that ball of charge, but inside the ball of charge, I can get a more interesting problem. So let me jump to that. So I want to go to the next page. Do I remember how to do that? Yes. So now I'm going to have a ball of charge, and that's got a radius of A. And now I have a point of interest, and that's R away. So now I do a Gaussian surface. Remember, you want your point of interest to be on your Gaussian surface so that Gauss's law applies to it. But now I use this radially symmetrical, spherically symmetrical Gaussian surface, but it's going through my point of interest again, which is now inside the charge. And watch how the problem just gets that bit more involved. So again, I have my E here, and I have my dA. And I say, well, okay, my flux is equal to the surface integral of E dotted with dA, which equals the Q inside over epsilon naught. And then I say, well, E is constant on Gaussian surface. And you can see, even though you're inside the charge, it's symmetrical. So that electric field for every point on this blue dotted line is going to be the same. It's not going to be the same as it would be outside at some point, but it's going to be of the same value. I don't know what the value is. I'm trying to find the value, but it's going to be constant. Is that agreed just from the symmetry? You can see that? So, and then we're also going to say, even now, even though I'm inside, E is parallel to dA. So my cosine theta equals 1. That's kind of nice. So I say my flux is equal to E integral of dA, which equals Q in over epsilon naught. Don't care about my flux. My E is equal to Q in over 4 pi r squared times epsilon naught, just like before. I say, oh yeah, KE is equal to 1 over 4 pi epsilon naught. So E is equal to KE Q in over R squared. Well, hold on, that's the same answer. And here's the rub. Pardon? No. So here's the rub. Q in, so let's put this down in a different color so that we kind of get it. But Q in is not equal to Q. Q's the whole thing. Q equals 6 coulombs, if you like. Q in does not equal Q. It's the Q inside the Gaussian surface. That's Q in. And so now I've got to do, oh, it's not as simple as I thought. I can't just substitute Q in for Q because it's not the same. In this previous example, Q equaled Q in because it was all inside the Gaussian surface. So now, because the Gaussian surface is inside the ball of charge, that's no longer the case. So what is Q in then? Q in is equal to, well, it's going to be the volume density times the d little times the little volume. And that's going to be, well, Q in is going to equal Q over, well, the volume of a sphere is 4/3 pi. Which am I going to use, A or am I going to use R for doing the volume density? It's going to be the volume of the charge, which is, the radius is A. So it's 4/3 pi A cubed times the little times the little volume. The little volume is 4/3 pi R cubed. Well, that equals Q R cubed over A cubed. The 4/3 pi's disappear. I substitute that in there. And then I get, well, in that case then, E is equal to KE Q R cubed over A cubed times R squared, which equals KEQR over A cubed. So there's my answer. And now you can substitute numbers in. So it's the same starting point. You just got to learn how to do this, you know. And it's, you know the math. It's just the volume of the little bit divided by the volume of the volume of the big bit divided by the volume of the big, the charge on the big bit divided by the volume of the big bit multiplied by however big the inside bit is. So it's the volume of the little bit. We did things analogous to this before in Physics 1. We did stuff analogous to this. Okay? I'm sorry? Yeah. Yeah, cool. So, okay. So that's where that comes from. Boom, boom. Not bad, yeah? Using method of Gauss's law that was shown in class, determine the electric field 2 meters from the center of a 4 meter. And let's have a look. I've only got half an hour. That's online. You can practice that. You can practice that online. Let's go to the next bit. Can you see how if I have a shell of charge, that if I'm outside the shell of charge, it's the same old, same old. You're going to work it out. You're going to have KE Q in over R squared, and all of the charges inside. So it's going to be the same, yeah? So that's a no-brainer. This is weird. This is saying the electric field is zero. Let's just see if I can figure that out from looking up here. So what that's saying is that rather than being a ball of charge, I have a shell of charge. So here's my, and I didn't color this in before because I wanted to make my diagram clear, but that's all charge. So I'm like in the middle of the earth gravitationally. This is a shell of charge. And my point of interest is inside. So can you see how much charge is inside that Gaussian surface? What's my Q in? Zero, isn't it? Because there's no charge inside the shell. It's like an eggshell. There's no shell inside the egg. It's all on the outside of the egg. So my Q is zero, so that Q goes to zero, so the answer goes to zero. But it's the same setup.
So there is no big Q on
No, a big Q is on the outside, but the big Q does not equal little q. Little q equals zero in this case. Now, I want to just point out two more things. Let's see if I can go back. For this one, let's say I ask you to draw a graph of my electric field versus radius. And let's say I tell you that the A is there. Okay?
For which equation?
For both of them. When you're inside, you're going to use that equation. When you're outside, you're going to use that equation. So outside, I know it's an inverse square law, yeah? Inside, how does this E change with radius? Remember, for a given problem, A is fixed. So how does, as you change R, how does E change?
Linear.
So it goes like that, doesn't it? Yeah? Now let's think about the gravitational analogy. If I go above the center of the Earth, if I go above the surface of the Earth, gravity falls off with an inverse square relationship. Isn't that what Newton told us? Big M, little m over R squared. Newton didn't think about going inside the Earth, and he didn't have the mass to go inside the Earth. But what this tells you is, if I go to the middle of the Earth, I've got no gravitational field. If I go halfway to the middle of the Earth, I have half the gravitational field. If I go a quarter of the way from the center of the Earth, 3/4 of the way in, I have a quarter of the gravitational field. If I go a quarter of the way in, which is 3/4 from the center of the Earth, I have 3/4 the gravitational field. So gravity gets less as you go deeper. What about this guy? What this tells me is that there's A. Inverse square relationship. Zero. The gravitational analogy, if we had a planet that was hollow and we just opened a trapdoor and went inside, we'd be in a space which has zero gravity field. So we'd have no weight. So we'd float around. So for all we know, the universe might be just a big drum with all the mass on the outside and an insignificant mass on the inside. It's kind of a frightening kind of prospect, but You want to work around high voltages, which means high potentials, which means high electric fields, but you don't want your hair to stand on end. Get inside a Faraday cage. Just get inside an enclosure which is metallized. So then you'll have no electric field inside. You can have all the electric field you like on the outside, but none on the inside. And that's called a Faraday cage. They build them around high voltage equipment. One of the problems you get actually with some modern construction is, from an energy point of view, it's nice to put aluminum foil on one side of drywall because it reflects the radiant heat. So you can buy drywall which has an aluminumized side on the inside wall side. And the problem is that you can end up with a room which is basically largely enclosed by these aluminum foil sheets. And if there's a little bit of moisture in the air, like there is in Britain a lot, you can have a kind of dampness which gives a pretty decent conducting path between all these aluminum foil sheets. And so effectively you're living inside a Faraday cage, which means that sometimes your radioception can be awful because you're effectively inside a Faraday cage, and you need the electric fields to get that. Let me talk you through this one. So just because I want to do one that's not symmetrical. So let's have a look at this. We have a infinite wire, and it has Q. No, it's got lambda. I'm sorry, charge density. Coulombs per meter. I can't talk about the number of coulombs because it's infinite. There's an infinite number of coulombs, but I can talk about a certain length. So it'd be lambda coulombs per meter. That's my charge. And I want to try and analyze this. I want to find the electric field at that point there. So I've got to have a Gaussian surface that goes through that point. I'm not going to use spherical symmetry because this is not a sphere. It's not a point. This is, if anything, like a cylinder, and there's a clue. So let's just make ourselves a cylinder. Nice and symmetrical. I still want it to be symmetrical. And I'll make this cylinder of radius r. There's my point of interest. And I know that my electric field is going to be radially symmetrical from the axis of the, so looking down from above, if I look down from above, my electric fields would all go like that. So I'm going to have an electric field is like that. And because it's the sleeve of the cylinder, my dA is going to be like that. And I say, okay, well, Gauss's law says that flux is equal to the integral of E dot dA, which equals Q inside over epsilon naught. And I say, well, I've got to divide this up into bits. Let's say A, B, and C. So let's look at this. For the electric field is going like that. But the area vector is going like that. So for A and B, E is perpendicular to dA, which gives us that our cosine of the angle between them equals 0. So no flux. So flux A equals flux B, which equals 0. So forget it. Yeah? Does that make sense? For C, E is constant because I did it as cylindrically symmetrical, and E is parallel to dA, So my flux is equal to the surface integral of E, so I'm going to do this again, I didn't, which equals Qn over epsilon naught. So my flux is equal to E integral dA, which equals Qn over epsilon naught. What is my surface area of C?
2 pi r
Times
times r plus h.
times H. So if that is H,
Oh, no.
yeah, and that is R. So flux is equal to E times 2 pi R, that's the circumference, times H, which equals Qn over epsilon naught. I say, well, in that case then, E is equal to Qn over 2 pi R H epsilon naught. Now I've got to do a little bit of head scratching here because Ke is equal to 1 over 4 pi epsilon naught. And so let's substitute for epsilon naught. Epsilon naught is equal to 1 over 4 pi Ke. Did I do that right? Yeah, just swap those two over. Yep. So E is equal to Qn over 2 pi R squared H times not epsilon naught. We're going to have 1 over 4 pi Ke. So that's Qn Ke. I'm sorry.
Why is it
The
R
R is not
squared?
sine, it's not supposed to be squared. And your E equals Q in to left, down, down, there you
There
go.
you go.
Should be squared, right?
Pi R squared. 2 pi R times
Area of the cylinder is
2 pi R.
just-
Thank you. Thank you, thank you, thank you. Thank you, thank you, thank you. So that's going to be Ke times 4 pi, that's that bit taken to the top, over 2 pi R times H. So let's have a look. The 2 pi cancels with that, leaving 2. So this is 2 Ke Qn over, did my R cancel?
No.
Over RH. So next I say, well, okay, what is my Qn? My Qn is equal to the length of this bit inside. It's the charge inside, so that's going to be H times my density of charge, lambda. Does that make sense? If I make a longer H, I get more charge. A smaller, we get less charge. So E is equal to 2 Ke H lambda over RH, which equals 2 Ke lambda over R. And is that what the answer is supposed to be? Yeah.
Is that one of the proofs that we have to do?
Yeah, yeah. That's what I'm telling you.
Okay, give us 17 seconds.
Cool. And then you should put numbers in. That one, don't worry about that one. Let's just, okay, because I want to, I've only got 10 minutes, but I want to set this up. Last little thing on this. When there is no net, so if I have charges on a conductor, they can move around. But they eventually stop moving around because they get to like an equilibrium position. So all the charges on the surface of this are going to spread out until then they're happy. Well, reasonably happy. And so we can say the charge is uniformly distributed, and it turns out it's not. Charges tend to congregate around points, and they tend not to congregate around flat areas. The field lines always approach at 90 degrees, and etc. This is very interesting. This is a very strong electric field. This is a very weak electric field around the same object. So you can actually make, like if you like, needles shapes will focus the electric field, and we use that all the time. We use that in photocopiers when we want to spray charge onto a piece of paper or something, and we use it in lightning rods. We use it on flat panel TVs when they have the little emitters, and they're all very sharp points to make the electric field very strong. So interesting stuff on that. And let's just stop that there.